Hi everybody, today we're going to be doing section 2.5 and we're going to be talking about rational functions. So a rational function is the quotient of two polynomial functions. So you have an a of x and a b of x. You divide them by each other and the result is your rational function. So what is the domain of a rational function? Well, we know that when you have a function in the denominator, that function can never equal 0. So the domain is all of the numbers excluding the ones where b of x is equal to 0. One important characteristic of rational functions is that many of them have asymptotes. And as you can see here, and as we've talked about countless times, an asymptote can either be vertical or it could be horizontal, and we're going to see later on that it could also be something else. All right, well, how do we find vertical asymptotes? To find the vertical asymptotes of a function, you have to simplify the function, then you have to find the zeros of the denominator. And I just want to remind you that this will give you any and all discontinuities. So you have to eliminate the ones which can be canceled. Those are the removable discontinuities. And the ones that cannot be eliminated are your vertical asymptotes. The horizontal asymptotes is a little bit different. To find the horizontal asymptote, you have to find the limit of f of x as x approaches infinity and negative infinity. Now, at infinity and negative infinity, remember, it's only the highest powers that really take effect. So for example, if your function is, x to the 5 plus 2x cubed minus x plus 2, when x equals 1,000,000 or 1,000,000,000,000, the only one that really matters is x to the 5, because 1,000,000,000 to the power of 3 pales in comparison to 1,000,000,000 to the power of 5. 1,000,000,000 to the power of 5 has 24 more zeros, so anything else pales in comparison. So really the only one we need to consider is the term with the highest degree from the numerator and the term with the highest degree from the denominator. Okay, so now, all you have to do really is you have to take the term with the highest degree on the top. So for example, suppose I had y equals x cubed plus x over x squared. All I have to do is take the term with the highest degree there, the term with the highest degree there, put them on top of each other, and simplify. And we simplify after finding a limit. So let's go and take some examples. Suppose you have a case, suppose you end up with something like this, x squared over x cubed. All right? What we want to do is we want to find the limit of this as x approaches infinity. Now, once you simplify this limit as x approaches infinity, what do you end with? These cancel, so you have 1 over x. All right? When x now becomes close to infinity, so when it's 1 over 1,000,000, 1 over 1,000,000,000, the entire fraction is going to be close to 0. So here the asymptote will be y equals 0. So this is the case when the denominator has a bigger exponent. Your asymptote is always y equals 0. Okay, what if the exponents are the same? So what if you have the limit as x approaches infinity, 2x squared over 2x cubed? Then these cancel and you just end with 1. So the asymptote is y equals 1. Now what if the numerator has a higher exponent? Well, in that case, There is no horizontal asymptote. All right, so let's take a look at these. It says to find the domain and the vertical and horizontal asymptotes of the following functions. Okay, well, domain first. You look at the numerator. The numerator is a nice polynomial function. There are no restrictions, so the domain for the numerator is all reals, but the denominator is a problem. Remember, the denominator cannot be 0. So 2x squared minus 34 cannot be 0. 2x squared cannot equal 34. X squared cannot equal 17. So when you take a square root, x cannot equal plus or minus the square root of 17. So what's the domain? Well, it's negative infinity to negative root 17. Negative root 17 to positive root 17. And positive root 17 to infinity. That's the domain. Now, let's talk about the vertical asymptotes. Well, these are where the denominator equals 0. So it's going to be x is equal to root 17. X is equal to negative root 17. You can also write this in more concise form as x is equal to plus or minus root 17. But if you don't have the x equals to, then it's not an equation, so it can't be completely correct. All right, what about the horizontal asymptote? Well, in this case, what we're going to do is we're going to take the limit as x approaches infinity. And now we're going to take the term with the highest exponent on top, the term with the highest exponent on the bottom. So it's 5x squared over 2x squared. And because the horizontal asymptote is a horizontal line, then its equation is not going to be x equals, but y equals. So in this case, what happens here? The x squares cancel, and all I'm left with is 5 over 2. So the asymptote is y equals 5 over 2. And that's that. Let's take a look at this one. All right, so there's a small typo here. And it's supposed to be that this entire thing is over 2x squared plus 1. Okay, let's take a look at the domain. So let me just rewrite this. It's 4x squared plus 3, 2x squared plus 1. Let's take a look at the domain. The numerator is fine, and the denominator. Let's talk about when the denominator can equal 0. Well, let's see. 2x squared plus 1 cannot equal 0. 2x squared cannot equal negative 1. So x squared cannot equal negative 1/2. Okay, there is no way to solve this because if I take a square root, then I'm going to get an imaginary number, which means there are no real values for which the denominator is 0. What does that mean? That means the denominator can never be 0. So the domain is all reals. Okay, if the denominator can never be 0, then what is the vertical asymptote? It has no vertical asymptotes. All right, well, what about the horizontal asymptote? Well, we're going to take the limit as x approaches infinity of 4x squared over 2x squared. So y is equal to 2. This next one, let's see what the domain is. Equals 0. 2x is 34. X is 17. So when x is 17, the denominator is 0. So it cannot be 17. So the domain is negative infinity to 17. 17 to infinity. Vertical asymptote, x equals 17. Horizontal asymptote, y equals the limit as x approaches infinity of 6x squared over 2x. Now, since there is a higher exponent in the numerator, there is no horizontal asymptote. We'll learn later on in this lesson that that's actually something else. All right, another one here. Let's see where the denominator equals 0. Okay, we factor. So the denominator is equal to 0 at -4 and 2. All right, so what I'm going to do here is write the factored form of this. Now, at x equals -4 and at x equals 2, there are discontinuities. The denominator is 0. That means my domain cannot include -4 or 2. So it goes from -infinity to -4, -4 to 2, and 2 to infinity. That's the domain. All right. Well, what about the vertical asymptote, though? Well, now you have to see. Is there anything here that cancels? Well, it turns out there isn't anything that cancels. So both of these qualify as vertical asymptotes. So you have vertical asymptotes at x equals -4 and at x equals 2. Well, what about the horizontal one? The limit as x approaches infinity of x over x squared. And since the denominator has a higher degree, we just say y equals 0 is the horizontal asymptote. All right, so how are we going to graph this? Well, first let's figure out the domain and the vertical asymptotes. All right, when we factor this, we get x minus 2, x plus 2. So the domain is anything except plus or minus 2. So it goes to -2, from -2 to 2, and from 2 to infinity. Now, the vertical asymptotes are x equals plus or minus 2. So why don't we draw them here? At x equals 2, there is a vertical asymptote. At x equals -2, there is another vertical asymptote. Now, are there any horizontal asymptotes? Well, yes, because y equals the limit as x approaches infinity of x over x squared. So at y equals 0, there is a horizontal asymptote here. Now, in order to graph, we need a couple of things. We need to know, first of all, what are the zeros? Are there any zeros of this function? Please, please, please remember that asymptotes, horizontal asymptotes, take effect only at the infinities. So here in the region, but close to the origin, the function can cross the asymptote 1,000,000 times. It's only at the very ends that it has to follow the asymptote. All right, so let's see if there are any zeros. To find the zeros, I need to set f of x equal to 0. So x plus 1 over x squared minus 4 equal to 0. When you cross multiply, x plus 1 is equal to 0, so x equals -1. So at x equals -1, there is a 0. All right, and again, it can happen. Okay, let's pick some other points. Let's see what the function is at x equals 0. When x equals 0, so basically what I want to do now is just pick a few points to gauge how my graph is going to look. At x equals 0, f of 0 is 1 over negative 4, so it's negative 1 over 4. Well, what's f of 1? F of 1 is 2 over 1 minus 4, negative 3. So that's negative 2 over 3. Okay, now, this sort of gives me an idea of what's happening, all right? Because I know that my graph has to follow the asymptotes, the vertical asymptotes. And I know that it needs to cross the 0 there. So if it crosses the 0 and it's going below, now I know that it has to follow the asymptote here. And if I'm going to the left, then it has to cross the x-axis and go up and follow the asymptote on this side. Now, these functions are like the old Atari games, where basically when a character goes off screen on one side, it re-enters on the other side. Okay? It re-enters on the other side here, so it's going to follow the asymptote. And now, eventually, there are no more zeros, so it's not going to cross the x-axis anymore. So eventually, it needs to level off here. Again, if this went off the grid here, it needs to re-enter on the opposite side there. So it'll look like this. Okay? All right. So let's do one more. To get a really accurate picture, let's factor everything here. X minus 4, x minus 3, and here, this is 2 times x squared minus 4, which is 2 times x minus 2, x plus 2. All right, so domain, right? It can't be plus or minus 2. My vertical asymptotes are x equals plus or minus 2. What about horizontal asymptote? For the horizontal asymptote, y equals the limit. I'm going to go to the original function, x squared over 2x squared. And as x approaches infinity, this is just y equals 1/2. So at y equals 1/2, I have a horizontal asymptote. And a vertical asymptote here. And another vertical asymptote there. Now, where are the zeros? Well, I have a 0 at x equals 4, x equals 3. So at x equals 4, x equals 3. Oh no, I'm sorry. This is positive 3. So here it's at negative 3. Okay, so already we can sort of see that it's going to cross the x-axis at 2 points here. Okay. All right, well, what else are we going to do here? All right, so here we know that if it's going to cross the x-axis here, then it sort of has to live on the bottom here, and it has to live on the bottom on the left side as well. In the middle here, there are no zeros. So in this region, there are no zeros. That means the graph never crosses the x-axis there. Okay, so let's just plug in a value here. Let's see what f of 0 is. Well, f of 0 is negative 12 over negative 8, which is a positive value, right? Negative 12 over negative 8, if we divide by 4, it's 3 over 2. So it's a positive value. So at 0, it's 1.5 right there. All right, so what does that mean? If it has to follow these vertical asymptotes, and it never crosses the x-axis in this region, and if it's got a point right there, that means it's got to live only in this region. So it comes over, turns around, and goes back. There is no other option for this. If you can come up with a different configuration, given the limits, you're more than welcome to bring it up. Okay? So now, just like I said before, if it goes off the grid here, then it must re-enter on the bottom. It's going to come up, hit that x-axis, and follow the asymptote above the x-axis at 1/2. And if it goes off the grid on this side here, then it must re-enter here, hit the 0, pass, and follow the asymptote. All right, so there is one other thing, is an oblique asymptote. So remember we said if the numerator has a higher degree, then there is no horizontal asymptote. Well, because in that case, there is an oblique asymptote. However, the condition is the numerator can only have a higher degree by 1. So numerator has higher degree by 1. For example, a function like this, x squared over x. So it's x to the 2 on top, x on the bottom. Or if it's x to the 4 on top, x cubed on the bottom. All right, so take a look at this one here. Vertical asymptote is... All right, now let's factor the numerator here. So we have x plus 3 here, and this numerator cannot be factored, so we're not going to factor the numerator. Okay, so what is our horizontal asymptote? Well, there is no horizontal asymptote. The oblique asymptote can be found by dividing these two. So you either have to do long division or synthetic division. In this case, we can do synthetic division, so why don't we just do that? So 1, -3, -2, 6, and we get a remainder of -4. You can get a remainder, that's totally fine. Okay, most of the time you will get a remainder. So when you divide, what do you get? You get x minus 2, and then the remainder, so it's -4 over x plus 3. This is your oblique asymptote. So y is equal to x minus 2 is your oblique asymptote. So what do you do with this? Well, let's see. We're going to graph it just like we do any other line. So y equals x minus 2 has a y-intercept at -2 and a slope of 1. So there is my oblique asymptote. Okay? Now, I also have a vertical asymptote at -3. All right? And now, why don't we pick some values here again? So let's see what f of 0 is. Well, f of 0 is -8/3, which is -2.67. So it's somewhere here, below. All right, so it's below the asymptote there. And let's see if we can figure out the zeros of this function. Well, the zeros are going to be where the numerator is equal to 0. And you can use your calculator, like you can graph that function to figure out where the zeros are. And there are zeros at -3.37 and 2.37. So -3.37 here and 2.37 there. All right, so what does that tell us? That tells us that here on the bottom there is a graph which looks like this. Okay, and there is another one here. All right, and that's what that looks like. Okay. All right, one more. So there can't be any graphs in this region because then it wouldn't pass the horizontal line, the vertical line test, and it wouldn't be a function. The same with this. If there were any graphs there, it wouldn't pass the vertical line test. Okay. All right. Now, we sort of touched upon this before. When the numerator and the denominator have common terms, which can be eliminated, there are removable discontinuities called holes. So let's take a look at this one here. When we factor the numerator, we get x minus 3, x plus 3. And here we get x minus 3, x plus 2. Okay, so what does that tell me? When these cancel, that means that x equals 3, there is a removable discontinuity or a hole. Okay, at x equals negative 2 here, because that never goes away, there is a vertical asymptote. Now, are there any horizontal asymptotes? Well, let's see. Y equals the limit as x approaches infinity. X squared over x squared. Yeah, at y equals 0, there is a horizontal asymptote. So at y equals 0, we have a horizontal asymptote. At x equals negative 2, a vertical one. At x equals 3, there is a removable discontinuity. Okay? And then where are the actual zeros? Well, look, from here, we can figure out that at x equals negative 3, there is a 0. Okay, now, so at x equals 3, somewhere on this vertical line, there is a hole. But where is it? Okay, to figure out the y value of the hole, what we're going to do is we're going to plug 3 into the simplified equation. So that will be 3 plus 3 over 3 plus 2 at 6 over 5. All right, so that's 1.1 right there. There's a hole. Okay, like that. All right, so how are we going to graph this one? Well, here there is a vertical asymptote, passes that hole, continues along the asymptote, and here it's going to come down here. Past this, but now it's got to go back and follow the asymptote. And you can always use your graphing calculator to help you check. All right, let's solve some of these functions. To solve rational functions, we have to multiply each term by the LCD of all the terms, and then we have to check for extraneous solutions. So here, I have a numerator of 1 and an x minus 6. The LCD is x minus 6. And now, what about any restrictions? Well, this function cannot exist if x was 6. So for the restrictions, we say x cannot equal to 6. So now I'm going to multiply every single term here by x minus 6. Every single term. Right, these cancel. So I have x times x minus 6 minus 4 equals 0. X squared minus 6x minus 4 equals 0. So here, can we factor this? I don't think so. So we're going to have to use the quadratic formula. 6 plus or minus the square root of b squared minus 4 times a times c all over 2. 36 plus 16 is 52 all over 2. And 52 is 2 root 13 over 2. So this is going to be 3 plus or minus root 13. Okay. One more time. One more. All right, here we're going to factor this. So we get x minus 6 and x plus 3. And it just so happens that that's the LCD. Cancel these. Okay, what do we get? 2x, x minus 6, plus 3, x plus 3. Is this so 2x squared minus 12x plus 3x plus 9 equals 27. 2x squared minus 9x minus 18 equal to 0. All right, so this is 2x, x plus 3 minus 6. So x equals negative 3 over 2, and x equals 6. All right, now what were our restrictions here? That x cannot be negative 3, x cannot be positive 6. So that crosses that out. My only answer is x equals negative 3 over 2. All right. So here, the lens equation is this, where f is the focal length, di is the distance from the lens to the image, here. Do is the distance from the lens to the object. Suppose the image is 10 centimeters from the lens. So the image is 10 centimeters from the lens. That means di is equal to 10. And the focal length is 6 centimeters. It says write a rational equation to model the situation. Okay, let's write a rational equation. Well, it's 1 over f equals 1 over di plus 1 over do. It's just plugging in. 1 over 6 is equal to 1 over 10 plus 1 over do. There we go. And now it says find the distance from the lens to the object. So it's, what is do? Well, okay. So my equation is 1 over 6 plus 1 over 10. Equals 1 over 6 plus 1 over do. 1 over 10 plus 1 over do. My LCD is 60. Well, it could be 30 as well. So let's multiply by 30. All right, so what do I have here? 5 equals 3 plus, I made a mistake. So it's 30D0 is my LCD. that means this is 5d0 equals 3d0 plus 30. Okay, 2d0 is equal to 30. So do is equal to 15. So it's 15 centimeters. All right, thanks everybody. See you in class.